how regularly you join. So today we have Villatoro speaking, and he will talk about integrating singular foliations with path. Joel?
So first I'd like to say thank you for inviting me to go on this fishing expedition. One thing I will say as a warning is I'm not going to talk very much about Poisson geometry, so there's not going to be a lot of fish on this fishing trip. But I mean, it is a topic sort of indirectly related to Poisson geometry, and so I think it's fair to bring it up here. So what I want to talk about is the notion of singular foliations and trying to understand how far you can get if you pretend a singular foliation is a Lie algebroid. That's basically, philosophically, that's basically where I'm coming from. Okay, so the general outline. First, I'm going to just talk a little bit about what a singular foliation is, and then I'm going to talk a little bit about Lie algebroids because, of course, the goal of this talk is to try to see to what extent singular foliations are like Lie algebroids. So let's write down some things about Lie algebroids as well. And then I'm going to talk about what should a morphism of foliations be. And this is, I think, not actually a trivial question when you go to the singular world, and you'll see that later. And then after that, I'm going to talk a little bit about sort of how do you understand what holonomy is of singular foliations, and then I'll look at some examples. Okay, so singular foliations. Just to establish some notation throughout this talk, M is always going to be some connected, smooth manifold. If I write this fractor xm, that means it's the sheaf of vector fields. And then I'll write the sheaf of C infinity of smooth functions with that notation right there. And so classically, a foliation is like an involutive subbundle of Tm, right? Where involutive means that sections, taking Lie brackets of sections gives you another section of the subbundle. What I'm going to do is I'm going to give a definition of a foliation from a module point of view. And so this is, I think the module point of view is the one that makes it easiest to sort of pretend they're Lie algebroids. So that's why I'm doing this. But it's going to look a little bit funny maybe to some people if you're not familiar with this stuff. But so for me, a singular foliation, or just a foliation, is a subsheaf of vector fields, and I want it to have a few properties. So one is the classical involutivity condition, right? That taking Lie brackets stays inside of this subsheaf. The other condition is that it's it's a submodule, so it needs to be closed under multiplication by smooth functions, right? And then the last condition is what I call adjoint integrable. So this is not, I haven't seen this in very many places in the literature, but this is sort of like a working definition that I use that seems to mostly work for the things I'm trying to do. The problem, so why is this piece here? Well, if you just assume A and B, then you can get some pretty pathological objects. But if you add C, then things start to be a lot nicer, basically. So what is C?
Well,
yes?
well, if you look at the notion of singular foliation, that it's, for instance, the book of Weissmann, also has some kind of invariance, isn't it?
Yeah. So actually in the older papers, you're right. Like in a lot of the older papers, people use something that's very close to this definition.
Okay, it's the same as in Weissmann.
Yeah. I think probably you're right. I haven't looked at that book myself, but I do know. I'll mention this a little bit. But yeah, so that this condition here basically just says that if you take an element of the singular foliation and you push forward another element of the singular foliation by its flow, then you stay inside of the singular foliation, right? So in a way, actually, you can think of this as sort of like a strengthening of involutivity. It's not just involutive, it's like super involutive. And the reason that this doesn't appear in the classical situation is that when this submodule actually comes from a vector bundle, this condition C isn't necessary, it's automatic. So yeah, so you can do even better actually. If F is just locally finitely generated, so at every point there's a local set of generators in the neighborhood of that point, then C is also automatic. So that's why in a lot of the literature you'll see them, instead of having this C, they'll say finitely generated. I mean, that's my point of view anyway. So if you have a foliation, you can make sense of integral submanifolds, right? By just looking at like the pointwise spans of elements of the foliation, you get a distribution, right? And the leaf is just going to be a maximal connected submanifold that has that distribution as its tangent space, right? And the important thing is the thing that makes this a sort of a definition of a singular foliation and not a regular foliation is that the dimension of the leaves can vary, right? In other words, this distribution that you get by looking at the pointwise span at each point, the rank of that distribution actually changes. So it's not like a subbundle anymore. It's like some sort of ugly thing. And then, so I guess this is a theorem usually attributed to Stefan Sussman as that if you have a singular foliation, then there's a leaf through every point. In fact, actually, they use a slightly more general definition than the condition C that I gave earlier. But they actually only require that the distribution is stable under the flows of the foliation rather than the vector fields themselves, which is a subtle point. But one of the things about the studying singular foliations is oftentimes it's very easy to get tripped up on subtle points. So I thought I'd just mention that. So one important fact about the leaves that's maybe slightly less well known about singular foliations is that if you take a leaf and then you localize the sheaf to that leaf, so there's like a sort of normal process for localizing a module to a submanifold. If you localize the module to that submanifold, then what you actually get is a vector bundle, and that vector bundle is a Lie algebroid. So the takeaway is that if you have a singular foliation and you have a leaf, then every leaf has a Lie algebroid associated to it. Now, the Lie algebroid can change in rank. Some funny things can happen, so it's not as nice as it might sound at first.
Can I ask you something, Joel?
Yes.
You wrote this condition C, and you mentioned that finitely generated implies that.
Yes.
What's the simplest example of something that is satisfies C and is not finitely generated?
On this slide, you'll see one.
And does the theorem that you just stated hold also under the C condition?
Sorry?
The theorem that you just stated at the end of the previous slide, does it hold under condition C?
No, well, I mean, so the problem is, I mean, sort of, it depends on your definition of Lie algebra. Okay, I think I should say no, because if it's not locally finitely generated, then basically you end up with an algebroid of infinite rank. That's what you should think happens. So the minimal number of generators ends up being the rank of the algebroid. And so if it's not locally finitely generated, then the rank in practice can explode. Maybe there's some sense in which it's an infinite rank Lie algebroid, but there's not a lot of, I haven't really tried to do that or to think of it that way. So that's why this proposition requires finitely generated. Okay, so here's an example. If you have a classical foliation, then the sections of that involutive subbundle are foliation. If you have a Lie algebroid with some anchor, then you can look at the image sheaf, right?
Sorry to interrupt. Dima was asking in the chat, what is the motivation for considering infinitely generated modules? Like,
so on this slide, I'll have an example of an infinitely generated singular foliation that you might think, well, it's fair to consider it. But I think one good answer to that is basically that there is another point of view on what a foliation should be, and that's in terms of the partition into leaves itself, right? And you can have two different modules that have the same partition into leaves. So you could say, well, rather than looking at, a module, you should look at all of the vector fields which are tangent to that partition, right? And you can start with something finitely generated and then end up with something infinitely generated if you look at all of the vector fields tangent to the leaves. And so if you think from a partition point of view, it's more natural in a way to allow infinitely generated things. And if you think from a module point of view, then infinitely generated things make your life worse. But
well, yeah, actually, yeah, I was aware of that. Thank you for your answer. I was aware of that situation, and actually, that for me was the reason not to go with that definition of a foliation, and rather to stick with with a module point of view.
Yeah.
Maybe for people like in control theory, the geometric point of view is more natural.
Yeah. So what I'd like to argue a little bit is that if you use the condition C that I mentioned, you can actually get surprisingly far with a lot of the stuff that people do for finitely generated, like a lot of the constructions. One of the points of what I'm going to talk about is that actually you can make sense of it outside of the finitely generated context, and it still kind of works. So I guess one hope is that is to try to understand how to unify this sort of like geometric point of view of the partition versus the module point of view. That's one of the things I'm hoping that sort of this goes in the direction of eventually. So one example of something that satisfies condition C but is infinitely generated is just take all vector fields on the plane that vanish at the origin. This satisfies condition C. The flow of a vector field that vanishes at the origin preserves that property, but it's infinitely generated in general. I mean, it's not completely obvious that this is infinitely generated, but it's an example. So an example that's not adjoint integrable is something like this, where you consider, consider vector fields where, like, on the plane where on the positive half plane for x greater than 0, the y portion of the vectors is 0, right? So on the positive half plane, all of the vectors are sort of horizontal, and then for the negative half plane, it's all vectors. Then you can show that this is actually involutive, that it's preserved under taking brackets, but actually it's not preserved under flows, because you can always sort of flow your vector field to the right and leave this universe of vector fields with this property. This isn't my example, and it's been mentioned to me by other people, and I don't know really who to attribute it necessarily, but who was the first person to mention this example. But this is sort of a classic example of why you shouldn't just assume involutive.
Joel, sorry.
Yes.
One brief question. The example with a joint integral but not infinitely generated, it looks almost like something that could come from a Lie algebroid or something like that. I mean, you have x dx, x dy, y dx, and y dy. Is there a reason why they don't generate it?
I don't think that set generates all vector fields that vanish at the origin is the problem. I mean, it generates the same tangent space, but I don't think it's all vector fields that vanish at the origin. Like, can you make the rotation out of that? Like, there's I don't remember exactly how the argument goes for this. This is something that
rotation like x dy minus y dx.
Yeah. Yeah. Okay. Rotation. Yeah.
I think in this case, Leonid is right, but
okay. So
you can have vanishing on a manifold. Yeah, I think vanishing on a submanifold maybe that's not.
So I remember this coming up in another context. Somebody told me it wasn't finitely generated, but to be honest, I didn't actually check myself.
I think if you say you want all vector fields to vanish at infinite order in the origin, and then it's probably it's infinitely
Sure,
generated.
I mean that is an example. That is an example that works.
Okay. Yeah.
Yeah. And it doesn't have to be R2, yeah. But if you look at things that vanish to infinite order, that's right. Yeah. That would be an example of that. So let's think about Lie algebroids for a moment. So a Lie algebroid, as probably most of the people in this audience know, it's a vector bundle with a Lie bracket, and it has a bundle morphism from the algebroid to the tangent bundle that has this nice Leibniz type property, right? And so a morphism of Lie algebroids is a vector bundle map that's compatible with these structures. And I'm not going to say yet what I mean by compatible. But what I'd like to say for now is that the definition is kind of complicated. It's not so simple. It's actually not so simple to write down, and it's kind of fussy, but you can we'll see something that looks like it later. So if you have any manifold, of course, the tangent bundle is an algebroid. If you have something like a Lie algebra acting on a manifold, then you can look at the trivial bundle, and that gets a Lie algebroid structure. So you can talk about homotopy theory for Lie algebroids by basically thinking, okay, well, the tangent bundle to a manifold is a manifold, right? And homotopy theory is basically at the most basic level, it's to try to understand a space by looking at all of the maps from like some model space into it, right? And in particular, most often is things like intervals and cubes, simplices, or spheres. And so the idea of homotopy theory for Lie algebroids is to say, okay, well, let's try to study our Lie algebroid in terms of maps from the tangent bundle to some model spaces into the Lie algebroid, right? So in particular, let's think about cubes, right? So definition, an algebroid path, called an A path in a lot of the literature, is basically an algebroid morphism from the tangent bundle to the unit interval to A. An A cube is the generalized version where you just take tangent bundle to a higher product. An A sphere is where you take the tangent bundle to the sphere. And an A homotopy is going to be something like if you have two different algebroid morphisms, a homotopy should be a map from the product of the domain with the tangent bundle to the interval into A that has the appropriate boundary conditions. I'm not going to write down the boundary conditions here, but just like regular homotopy, just like how you usually require boundary conditions for homotopy theory, there's the appropriate boundary conditions hold in this case as well. So I guess one thing I should say about this first is that because the definition of a morphism of Lie algebroids is kind of complicated, these things are all also kind of complicated objects, right? And so when I just say that it's just this, and it's just this, and it's just this, I'm sort of hiding a lot of, like, in order to really make things work and check all the technical details, it can sometimes actually be a lot of work to really verify all of that this has all the properties that you want. But after doing all of that work, you can show that, that if you study based A spheres modulo A homotopy, then those are well-defined groups. And if you take A paths modulo A homotopy, that makes a groupoid. And I prefer to call it the fundamental groupoid of the algebroid. Some people call it the Weinstein groupoid. But I like the term fundamental groupoid because it sort of emphasizes the way that it generalizes the fundamental group of a manifold. Now, suppose you have a smooth manifold. And then the homotopy groups of that are just the classical ones. That's because a morphism from the tangent bundle to M to the tangent bundle to N as an algebroid morphism is just the same as a smooth map. If you have a Lie algebra, you have some more interesting things happen. So if you take a Lie algebra and you look at the fundamental groupoid of the Lie algebra, well, if you think of a Lie algebra as a algebroid, it's an algebroid over a point, right? So the fundamental groupoid should be a fundamental group. And it turns out that the fundamental group is just the simply connected group that integrates that, or it is a simply connected Lie group that integrates that. And in general, if you go to the higher homotopy groups, what you'll get is the homotopy groups of the simply connected integration. So in particular, I guess for n equals 2, this is trivial. In general, this is like pretty hard to compute, just like homotopy. I mean, it's even harder to compute, right, than homotopy groups for manifolds, because morphisms of algebroids are kind of annoying. But topologically, what you can say is that this thing is always discrete when n is greater than or equal to 2. And when n equals 1, the fundamental group of the algebroid can be topologically pathological. But in the nicest case, it's going to be a smooth manifold, but not necessarily discrete. So properties of this thing, the orbits of this fundamental group are just the leaves of the image foliation for the algebroid. Right. So I mentioned earlier that from a Lie algebroid, by looking at the image of the anchor map, you get a foliation, and that's what you get. When the fundamental group is smooth, then you can get an identification between right invariant vector fields and sections of the Lie algebroid. And so that tells you that really this generalizes the notion of integrating the Lie algebroid, right? Because it's the right invariant vector fields. And of course, the source fibers are simply connected. So for example, in this case where we were looking at the Lie group, right? The source fibers are just the entire space because there's only one point, and that's simply connected. So now I'm going to try to say, okay, how do you try to tell this story for foliations? So in order to do that, what I want to know is what is a map from the sheaf of vector fields on the unit interval to a foliation? How should one imagine what that should be? And in order to make sense of that, I'm going to use the notion of a pullback module. Okay, so if you have a sheaf of modules on M and you have another smooth map into M, then there's a notion of the pullback module, right? And the pullback module is constructed as basically a tensor product of the sheaf of smooth functions on N with the pullback of the module E, or the pullback of the sheaf, right? So the important thing is that this is not, right? This is not just the pullback sheaf. This is not just the pullback sheaf, right? It takes into account the module structure. And the end result is a C infinity of N module over N.
I mean, the pullback sheaf wouldn't be a C infinity of N module, right?
Yeah, exactly.
Sheaf. But if you generate a sheaf of C infinity of N modules out of that, don't you get this one?
Yeah, basically. That's basically it, yes. I mean, that's more or less what this tensor product is doing. You pull back E, and what you can think of that as giving you a sheaf of the pullback of C infinity of M modules. So this is like a new sheaf of rings on N, which is the pullbacks of functions, right? And then you take the tensor product here, and then that sort of kills off some things, it invents some new things. So near a small enough open, this has a reasonably simple form, right? You can always write it down like some collection of functions inside of smooth functions on N, and tensored with some elements of the sheaf on M. Okay. So near a small open U, it really looks like this nice sort of finite sort of C infinity of N linear combination of elements of N. which is, I guess, what Marius was just saying. If you take basically the case where E is actually the sections of a vector bundle, then this pullback module is canonically identified with the sections of the pullback of the vector bundle, right? So the point is that this is basically just the pullback vector bundle in the language of modules, right? Now, suppose you have a foliation on M and you have another foliation on N. A morphism of foliations, right, from N to M is going to consist of the following. So this is my proposed definition for morphism of foliations. It's a smooth function, one from M to N, and a morphism of C infinity of N modules from the domain foliation to the pullback module here, right? So the important thing is this is not a foliation. This is not a foliation. This is just the pullback of some module, right? And this is a morphism of modules over N.
There is a typo, no? M and N are interchanged.
Yes, I think this should be N. This should be M, like this. Thank you. So that's going to go away. So I'm not going to bother trying to write that again, but please remember that. So this obviously has to have some properties, but one thing is I'll say about just from this setup, if these two foliations were the sections of some vector bundle, then this condition here is basically just saying that there's a morphism of vector bundles from one to the other. Because a morphism of vector bundles, say from E to W, this is the same as a morphism of vector bundles from E to the pullback bundle W. It's the same thing, right? So this is just saying morphism of vector bundles in the language of modules. Now, compatibility with the inclusion. So this is like, you should think of it from the Lie algebroid point of view, this is like saying compatible with anchor, right? You have this nice commuting diagram of the vector fields on N, the vector fields on, or the foliation on N and the vector fields on N. But then there's also this pullback of the inclusion from M to the vector fields on N. And another warning that I'll give is that this is not injective in general. It's not the case that if you pull back the inclusion, that you'll get an injective map. It's just something that's true about, it's just something that happens with modules. So the point is, compatibility of the inclusion is not like a trivial condition that automatically comes from, you know, the smooth function being around and the inclusions being around. Now, there's the other condition, which is compatibility with the brackets. And if you're familiar with the definition, with the sort of ugly definition for a morphism of Lie algebroids, not the sort of nicer definition in terms of the complexes, this is just basically that exact definition. That if you have a vector field if you have something in your foliation on N, and you look at it, and you push it forward to this thing, right? It's like this sum of tensor products. And you have another expression like this, then there's some condition involving the brackets. It's something like, you know, that you sort of pretend there's a Leibniz identity and you write down what it really should be if, you know, the Leibniz rule was in effect, if everybody was an algebroid. Yeah. So Dima in the chat is exactly right. So this is basically just saying that this is a morphism of sheaves of Lie-Reinhardt algebras. Yeah, I should have said that. So this is a morphism of sheaves of Lie-Reinhardt algebras, basically. So this is a proposed definition for what a morphism of foliation is. And one thing that I will say is that all of these conditions are not sort of trivial. You can come up with examples where, you know, this holds, but this doesn't hold, or that this holds, but this doesn't hold. There are bad examples that sort of show that these conditions are not trivial, that you really have to enforce them. Which is in contrast to the case of regular foliations, where really this is kind of, these conditions are very automatic, because the only reasonable map at the level of the vector bundles for regular foliations is just the push forward of the tangent bundle. So
can you talk about foliated cohomology so that we can use the foliated round complex maybe?
yeah, so this is a very reasonable question. I'm glad you asked. So the problem is that the dual, if this is not a vector bundle and you take the dual, then the dual can be very bad, even if you started with something that's not so bad. And so it's not the case that, you know, there's a dualization functor, right, that goes from one to the other, but it's not the case that a morphism after taking the dual is going to coincide with a morphism before taking the dual. So what I'm saying is that you can write down a definition in terms of what you said, but they are two different definitions. They're not the same thing in general.
Well, I guess it depends also on how you define dual, because you have the freedom to make sense of the dual in different ways, I guess.
Yeah. The problem basically is that that the correspondence between the complex definition for the algebroid morphism and the sort of more straightforward vector bundle definition is that that correspondence relies crucially on the fact that these are locally free sheaves, basically. That correspondence is just like not true if these things are not nice, locally free, finitely generated sheaves.
What I also have a question.
Yeah.
Hi,
Rui.
Hi, how are you? In the finitely generated case, can you simplify this definition, or is in particular you have these algebroids on the leaves? Does this amount to some kind of algebroid morphism between the algebroids of the leaves?
Yeah, actually, I mean, that's something I should have mentioned. If you take this definition, then if you have such a thing, then you do get morphism. You here some facts that I didn't remember to include in the slides. The map sends leaves to leaves. So the compatibility with the inclusion will imply that leaves get sent to leaves. So you get a map at the level of the leaves, and you also get a map at the level of the leafwise algebroids. Now, the problem is you could try to say, well, what if you just sort of have a map at the level of leafwise algebroids? But the problem is, like, you should have some sort of transverse sense in which that's smooth, because the leafwise algebroids can't be put together into like a global thing. And so this is giving you a way of saying, you know, there's like a sort of there's like a global way of saying morphism.
But in the previous slides, you have the first two conditions, which are very natural, as you were saying, and now you can replace the next ones by saying that what exactly you just said, that they map leaves to leaves and that they are morphism of algebroids, no?
I haven't thought about trying to see if the relationship between defining it that way and this way. So I'm not sure actually what happens. Like,
okay.
My instinct is that you won't get the same thing, but I'm not 100% sure, so I'm not sure. I think from like an algebraic point of view, this definition really makes a lot of sense.
Joel,
yes.
In the chat, Luca was asking whether in principle you could define singular foliation starting from differential forms instead of vector fields. Okay, I also see an answer in the chat, actually.
Yeah, so I mean, it's exactly what the problem is. Like, you could try to define it. Okay. Yeah, I think that you could try to define things this way, but I mean, the problem is that once you get to the singular foliation case, when you start taking the duals, you just get different definitions. And I think it's reasonable to try to say like a singular foliation should be some sort of like nice ideal of forms. That's like, you know, there's a definition of regular foliation in terms of like some ideal of one forms, right? Generated by some one forms, but like these are just not the same definition when you start allowing for these sort of infinitely generated singular objects. And like, yeah, you can define it that way. I haven't seen a lot of people using that definition, but I think it's interesting. But I guess what I'm saying is it kind of depends on what you want to do and what your definition of singular foliation should be, because the definitions tend to diverge.
The definition, I think, also is simplified when F is transversal to the foliation. When the map F is transversal to the foliation, you just have a map from the foliation of N to the pullback foliation on.
Yeah, you're right. Yeah, there are some nice things that you can say about this definition when F is particularly nice. Like if it's a submersion, the story becomes a little bit easier, things like that. Okay, so let's see some examples. So if you have two singular foliations and it happens that they are the sections of some vector bundles, right? In other words, the singular foliations arise as Lie algebroids with anchor maps that are injective on sections, right? Or almost injective Lie algebroids. Then the definition here is just exact same thing as saying it's a morphism of the algebroids. There's no difference. So here's an example of, so I mean, probably there's not enough time to really give people time to think of, to properly analyze this example, but if you want to sort of play around a little bit with this definition to understand what's going on, I do propose that this is a reasonable case where you take N and M to be R2, and you look at the foliation generated by these vector fields. Okay, and say that the function f is constant, right? So we have the tangent foliation on the plane getting mapped to a point, and the foliation in the codomain is by a point and then open set outside of that point. Then you can show that if you have the following rule for the morphism of modules, that this works, right? That this will define a morphism. On the other hand, if you had chosen something like this, then you would get a morphism of modules, but it would fail the bracket compatibility condition. Basically, the idea is that partial x and partial y in the domain, they commute, right? So in a sense, they should be sent to things that commute. And since these two vector fields commute, this is allowed and it will give you a perfectly well-defined morphism. But if you choose two vector fields that don't commute, then you'll fail the bracket condition. And so this gives you an example of something that satisfies all of the conditions except the bracket condition. In particular, in this example, the compatibility with the inclusion condition is trivial. There's nothing to check. Okay, so what do you get? So using this definition of singular foliation, or the morphism of singular foliation, you can say, okay, well, let's study singular foliations probed by intervals and write down the definition of homotopy. So I'm not going to write down exactly the boundary conditions that we use in the definition of homotopy or that, but just take my word for it that after doing some technical work, you can make perfect sense of an equivalence relation on morphisms of foliations from the interval to your singular foliation, and that you'll end up with a groupoid. And I call that the fundamental groupoid of the foliation. So here's basically a summary of some of the results that appear in the paper. So one is that if you take this fundamental groupoid, the orbits are exactly coincide with the leaves of the foliation. Even better, if you restrict to a leaf and you look at the leafwise algebroid, then it's actually the source simply connected integration of the leafwise algebroid. And the source fibers of these things are simply connected. I mean, that's sort of obvious from the previous bullet point. So one remark that's sort of special about this foliation case is that it happens that if you take this holonomy, oh, sorry, I forgot to mention this fourth bullet point. So there's another groupoid constructed out of a singular foliation called the holonomy groupoid that originally appears in a paper of Androulidakis and Skandalis. And so in our article, we show that there's a surjective groupoid homomorphism from pi1 of f, the fundamental groupoid of the foliation, to their holonomy groupoid. And so Claire de Board showed that if you take this holonomy groupoid of Androulidakis and Skandalis and you restrict it to a leaf, it turns out to be smooth. This is something special about the foliation, about foliations. And later on, so Androulidakis and Zambon, talked about this leaf-wise algebroid. They noticed that this holonomy groupoid, when you restrict to the leaf, is actually an integration of that. So in particular, if you take this fundamental groupoid of a singular foliation, sorry, this is all in the finitely generated context. I forgot to mention that. So at these points are about finitely generated. So these papers are all about finitely generated things. Right. But what I claim is my
Isn't
definition
the
of
whole
fundamental
theorem
groupoid makes
about
perfect
finitely
sense
generated?
without finitely generated. There's no need for finitely
Sorry,
generated.
well, isn't the whole theorem about finitely generated? Because there is also the leaf-wise algebroids in the very beginning of the statement.
Yeah, sorry. Yeah, you need up here is finitely generated. You're right. You don't need finitely generated for the first one. And in fact, this groupoid makes perfect sense outside of the finitely generated context, but you should expect it to sort of be an infinitely dimensional object in that case. It should somehow be like some sort of infinite dimensional thing. Okay, so in the finitely generated case, this thing is it turns out that if you restrict to a leaf, it's actually a Lie groupoid. It's smooth, which is a little surprising to me. I mean, not even every algebroid integrates to a smooth thing. So, and then one warning though is that even though when you restrict to a leaf it's smooth, it's not necessarily transversely smooth. So if you restrict it to different leaves, you'll get things of different dimension in general. And so there's not a transverse smooth structure in general. But in the article, we do mention how you can give it a sort of diffeological structure, just to say that there is some kind of notion of smoothness for it.
But it can be smooth for non-singular foliations.
Sorry.
Yes.
For regular foliations,
Or
it's
no,
always.
For singular foliations.
Yes, it can be smooth.
Yes.
So in particular,
But,
sorry, Alfonso, you can answer if you like.
For projective foliation, is it smooth, for example?
Yeah, so in the case of the almost injectively algebroid, it's going to be a smooth manifold. It's just a Lie groupoid integrating that almost injectively algebroid.
Is that the only case?
Yeah, I mean, if it's smooth, then there's an algebroid around. And
No, but is it true that it's smooth even only if the underlying foliation it's an almost injective is given by an almost injective algebroid?
Yeah.
Okay.
Yeah. The same is for Androulidakis and Skandalis group.
Yeah. So basically the problem is dimension. The dimension varies from point to point. If the dimensions all happen to line up, then smoothness happens. Really, it's just a problem that moving transverse to the leaves, the dimension jumps. Okay, so the last thing I really want to talk about is holonomy. So I talked a little bit about the fundamental groupoid of a foliation, but there's also another important groupoid associated to foliations, and that's the holonomy, right? And the classical version of holonomy is understood as you try to study how do paths in the leaves affect transverse slices. So how do they twist around transverse slices if you try to transport a slice along a path? And in the singular case, there is a holonomy groupoid that was constructed by Androulidakis and Skandalis. And it turns out that that holonomy groupoid does coincide with the classical holonomy groupoid for regular foliation, so it's sort of reasonable to call it the holonomy groupoid for a singular one. But their construction is quite different from the traditional one for the classical foliation. It has, it uses some sort of novel technology made specifically for it. Now, Androulidakis and Zambon in a later article, they showed that elements of this holonomy groupoid do sort of act on transverse slices. And so that's what we're going to see, how to understand the transverse action of a, and we're going to see a path model for how to understand the transverse action. So here's my working definition of slice for this. So a slice is basically just a submanifold that at a specific point is transverse, and away from that point, it's, at a specific point, it's a clean transversal, and away from that point, it's just a regular transversal. The reason that that we only say that it's a clean transversal at one point is, of course, the problem of the dimension varying. We can't expect it to be a clean transversal everywhere. So that's what this is saying right here. It's saying that the transverse is clean at some base point P, and outside of that point, it's just regular transverse. So if you have a slice, it turns out that it inherits a foliation. And so this is kind of a complicated thing that maybe I don't have enough time to really properly explain fully, but there is a subgroup of the diffeomorphisms of S that can be obtained by looking at the time one flows of elements of the foliation on the slice, but by elements of the form IPFS, which IP here is the vanishing ideal at the point P. So it's sort of like vector fields in the foliation that vanish at P in a controlled way. So if you have an F path, right? So the definition I gave earlier of a morphism of foliated manifolds, this is what you get. You get an underlying path, right? That's the base map at the level of the manifolds. But then you also have this phi, which is the morphism of modules. And if you write down what it'll look like this. You look at phi applied to the generator, and you'll get some sum of tensor powers of smooth functions on smooth functions on the interval with xi. Okay. And in particular, you'll get that if you look at this object here, you'll have a path where you take, so this is a consequence of compatibility with the inclusions, is that this path is actually an integral curve of this time-dependent vector field that you naturally get as a consequence of this part phi. So it's an integral curve of this time-dependent vector field. And so here's a definition. So an extended F path. So in the article with Alfonso, we call this an F path, but I'll call it in this an extended F path. So what that is just a vector field together with a path in M, where this vector field is time dependent. And there's a little bit of a subtlety in the definition of time dependence here, in that it should look something like this. And the path is an integral curve of that vector field. So what you should imagine is like, you have the path here, and then you have the time dependent vector field that's sort of defined around the path. So we're including the vector field around the path. It's like it has turbulence. So extended F paths, of course, can be used to define regular F paths. So let's look at holonomy. So suppose you have one of these extended F paths. Remember, an extended F path, you have a time-dependent vector field and a path. And suppose you have a slice at the start of the path and a slice at the end of the path. Then one thing that you could do is you could look at the flow of this vector, time-dependent vector field and see where does it send this slice. And in general, it may not send this slice to the slice you chose over here, right? They might not coincide. So in general, it'll end up being some other slice here. What this lemma says is that even though these two slices don't agree, there's always a nice choice of a vector field that sends this guy to here, that sends this slice to this one. There's an element Z of a specific kind that controls the failure of this slice to be sent to this slice. Now, the difference between the regular case and the singular case is in the regular case, this Z, you have very little choice for it, actually. But in the singular case, you may have many choices of Z. So in the singular case, there's sort of more ambiguity in what happens when you take this thing. So this is an important lemma to understand holonomy, right? So we're taking this extended F path and we're looking at what does it do to a slice. So if you have an F path in the situation of the previous lemma, you can define holonomy to be, well, you get a germ of a diffeomorphism from here to here. The problem is that you chose a Z in order to define this germ of a diffeomorphism. So you have to mod out by something. So what I'm basically saying is that you get the germ of a diffeomorphism. It's the one that sends this, this point on the slice to this point on this other slice. And then you mod out by the ambiguity that appeared in your choice of Z. And we say that two paths are holonomic if they define the same class inside of this. So that's the idea. And because in the regular case, like I said, there's not a lot of choice for this Z. So it turns out that this quotient, the sort of this part of the quotient ends up being trivial. You don't have to worry about it. And you can really just think of it as diffeomorphisms from slices to slices. But in the singular case, you can't get rid of this part. Okay, so the takeaway is the situation is more complicated for than for regular foliations, but you can still make sense of how does a extended F path act on the transverse geometry of the foliation? How does it act on a slice? And the theorem is basically that if you define this Colonomy property, it gives a well-defined equivalence relation on the extended F paths. That equivalence relation doesn't depend on the choice of extension. So that doesn't depend on the choice of extension. And so you get an equivalence relation on just normal F paths. And then finally, if you take the quotient of the fundamental groupoid modulo holonomy, then that defines a groupoid canonically. So this equivalence relation turns out to respect homotopy. Sorry, I forgot to include that, right? So the holonomy is implied by homotopy. And so that means that you can make sense of what it means by taking the quotient of the fundamental groupoid modulo holonomy, and that gives you a groupoid that's actually the same as the one of Andrewli, Dacus, and Skandalis. It's the same in a sort of canonical way. So if you take, so basically the conclusion is you have a groupoid homomorphism from the fundamental groupoid of the foliation to the holonomy groupoid of the foliation, as I just defined. And so as with regular foliations, so just one comment, as with regular foliations, going from a foliation to the fundamental groupoid of the foliation is a functorial process. But if you start with a foliation and you go to the holonomy of the foliation, that's actually not functorial in general. So if you want to see an example, look at the Mobius band and think about the inclusion of the zero section. So I guess I'll conclude the talk with just like a few examples of what kinds of things you get. So if you have a foliation, say you have an open leaf, then a slice through that point is just a point. And in that case, the holonomy is just always trivial. And the fundamental groupoid at a point in an open leaf is just pi1 of the leaf. More generally, actually, for a regular leaf, so a leaf that has sort of nearby is regular, the fundamental group and the holonomy groups are going to be discrete. It's not always discrete though. So for example, if you take something like SL2 acting on R2, the origin is a leaf. So a slice through the origin turns out to just be an open set containing the origin. And the leafwise algebroid over the origin is actually just SL2 itself. So if you work it out, you'll see it's SL2 itself. And pi1 of the origin is just the universal cover of SL2. And the holonomy is SL2. And you can see that this sort of makes sense, right? The universal cover of SL2 doesn't act, it has some kernel in the way it acts on R2, as so that you're modding out by some sort of kernel of its action on the space. And then, so finally, if you have a Lie algebroid and you look at the associated singular foliation, so if you're given a leaf, let A be the leafwise algebroid defined by the foliation, right? So B is an algebroid, A is the leafwise algebroid defined by its associated singular foliation, then you have some sort of groupoid, you have some groupoid homomorphisms from the fundamental groupoid of B to the fundamental groupoid of the leafwise algebroid, which is the same as the fundamental groupoid of the foliation restricted to L. And that comes with a homomorphism to the holonomy of the foliation at L. And so so that maybe what I should say is that it's reasonable to wonder what the kernel of this map is, the kernel of the composition here. And the kernel of the composition, I think, turns out to be an element of this is in the kernel if there's like a bisection that acts trivially on some transverse submanifold. So there's a bisection that that acts on some transverse submanifold that defines a diffeomorphism from a transverse submanifold to itself that's trivial. So it kind of makes sense to think of it as the holonomy of the foliation, because it's defined in terms of the transverse action. Okay, so that's the end of my talk. Here's a picture of a foliation.